So basically, what I'm hoping to do is kind of go through the history of that slides are not moving on the right line.
PCI Express, Penguidon 2013, Saturday at noon.
Trying to go. Oh, there you go. Goes. New PowerPoint is actually kind of cool. But yeah, it's 2013. Even newer. Yeah, Super Windows 80. So yeah, so we're going to go through like the history of PCI, how it kind of got us to PCI Express at this point. And at both stages, we covered the software layer behind it, and the hardware as well, some physical layer stuff, and how the protocol has evolved from its early beginnings. So PCI stands for Peripheral Connect Interface. It's developed at Intel Architecture Development Labs, which no longer exists. They did PCI and AGP before they were folded in some kind of political infighting at Intel. They designed it to replace the old VISA local bus, ISA, you guys ISA and other peripheral buses of the time. And it was an attempt to be truly plug and play. You just plug in the card and everything should work. So it removes you from the jumper hell that was common with ISA. You had to configure the card before you put it in, and if you move it from slot to slot, you had to deal with that. VISA was tied to the x86, the 486 specifically, and its memory controller. And then eISA was a political answer to IBM's MCA standard, and the clone PC manufacturers decided to come up with eISA, but it saw very limited adoption as well. So the idea behind PCI plug and play is PCI devices have their own memory space called config space or configuration space. And it's easy for your host device to go through and enumerate all of the PCI devices in a system, and then it can decide, okay, you get these resources, you get these resources, all without the user doing anything. Each PCI device is responsible for telling the host how much memory it needs, what interrupts it needs, etc. So all you have to do is depend on your system firmware to do everything, which in some cases, as you know, you can't really trust your BIOS to do the job right, especially if you're running Linux. So the software configuration mechanism, basically every PCI device starting at the beginning, you got 256 bytes for config data. So I think my next slide has an outline of what's in there. And then the latest spec allows each device to have 4 kilobytes of memory space to do whatever it needs to do. The header formats are standardized, and there's a concept called capability pointers where instead of being fixed, it basically points to, hey, go here for the next header, go here for the next header, or it'll just say FF and say, all right, config space is done. So it's very, very flexible. And the host access varies on platform. So on most x86 machines, these 2 I/O ports give you access to the PCI bus and config space. So these registers are, vector is not showing it really well, but basically these first 64 bytes are common. Basically you start with the device ID and vendor ID, which identify the device. So Intel, of course, gets hex 8086, and then the device ID, the 16 bits, so they can have 65,000 devices. Command and status registers are used during config space control, so you can command the device to enable itself, disable itself. You can check the status. And then we have revision ID, which is like the silicon revision. Class code, which isn't used too much these days, but basically says, hey, I'm a video device, hey, I'm a RAID controller, hey, I'm a network controller, things like that. And then right here is the first capability pointer. So if I'm parsing, and I get here and I see FF, I know I'm done because that's the end of config space. Or if I see, say, like 40 hex, then I know, hey, I should go to address 40 hex, and that means the device has more data to tell. So the type 0 header is used for most common devices. These are the specific things right here. So there's base address registers, which I think is the next slide. And then there's card bus specific stuff, which has died in death as we no longer use that. And then there's a few other things here like subsystem ID, subsystem vendor ID, and then the expansion ROM base address. So if you have an Ethernet card that can do Wake on LAN or something like that, this tells the hardware what address to jump to execute that expansion run. So base address registers, or bars, are kind of the secret sauce as to how plug-and-play works. So you can have up to 4 of these, and basically this tells the host, hey, I need a memory region of this size. So this is the breakdown of a 32-bit bar for a type 0. So you really only actually get 28 bits, but basically this is indicating that you want a memory bar, not an I/O bar. This says I can be in 32-bit space, I can be in 64-bit space. Prefetchable basically says, hey, you can cache this data, or no, you can't. So if you're doing an I/O card, you want this to be 0, otherwise you're never going to get the latest data. And then the base address, the way this works is the host device will write all ones to it, and then it'll read back from the register. And the device internally will tie down certain bits of this to 1, so the host will get some number of 1s back, and that determines how big the bar is. So the device is responsible for hardwiring those bits. The host writes all 1s, reads back, sees what it gets, and says, oh, okay, cool, you need a 1 gig bar, hey, you need 8 megs of memory. And the BIOS keeps that in mind when it's going to start allocating space. So that memory space is taken from your host memory space. So if you have a 32-bit box and you have 4 gigs of RAM, you're not going to be able to use all of it because some of that 4 gigs of physical memory space is getting assigned to your PCI devices. So if you have like a video card with a gig of RAM on it, you're going to lose a huge chunk of that memory space. So even if you have less than 4 gigs of memory, 64-bit OSs are very mature now. Everyone should be running 64-bit to avoid that. But this allows for memory mapped I/O, which is the most powerful feature of it. So let's say I have a PCI card and I memory map an address to it. I can just, in C code, get a pointer to that address, write to it, read to it, and that will do something on the device. So I could have an obnoxiously overcomplicated LED controller, and writing to an 8-bit register could control the value of 8 LEDs as fast as the CPU can read and write from memory, which is extremely fast. There are I/O bars for I/O space allocation, but they're not as frequently used. So x86 actually has 2 memory spaces. There's memory, like our RAM address space, and then there's I/O space, which is still limited to 64K. And that was used in the older days. You'd have I/O space for like serial ports, parallel ports, and things like that. So there aren't too many devices that need that these days, like video cards or maybe like a PCI Express serial card might use that, but it's not terribly popular anymore. The spec limits you to 255 buses, 32 devices per bus, and then up to 8 functions per device. And that's a hard limit. That's not changing anytime soon. So we use a shorthand BDF, or bus device function, to describe the location of PCI device. So kind of the standard Linux output format is like 0, 1.e. You're on bus 0, talking to device 1, function 14. But just because it gives a bus number, this doesn't actually mean there's a physical bus. For software purposes, like a lot of your processor internal stuff will be on bus 255, or every time you hit a PCIe port, your bus number increments by 1. So the bus topology, your root bus is always bus 0. So on most motherboards, your chipset stuff, your like SATA controllers, USB controllers, they're all going to live on bus 0. There's going to be different devices. Buses are spawned off through PCI to PCI bridges. So basically lets you tie a bus to another bus. And then, most common architecture is you throw your system and motherboard devices on the first 2 buses, and then you leave the rest of the buses available to expand off of. So your PCIe slots in your motherboard all will have their own bus number. The discovery mechanism, generally we'll do a breadth first search, so we're trying to go as deep as it can go to find devices before moving up, because each bus must be allocated a memory window that covers everything below it. So if you did it the other way around, you would end up not allocating enough resources or bus numbers to any devices. So here's a sample bus, which is like really tiny now that I think about it. But this is just LSPCI from my box. No one can see that, can they? No, that's too tiny.
It's there.
Yeah, it's there. Yeah. So let's go. So PCI local bus is the original PCI. So I just cribbed this from Wikipedia. Everyone's seen these slots, I take it. They've got different keys based on it being 3.3 volts or 5 volts. It started off as 32-bit, 33 megahertz. They later expanded to a 64-bit standard. It's a parallel architecture, which means that all the slots share these address lines. So you share 32 address and data lines. You share byte enables, you share the clock. And the way interrupts work is it swizzles it. So if each device, there's 4 interrupt pins. There's A, B, C, and D. And if most devices only implement interrupt A, but if you had every device sitting there on interrupt A, it would be pretty painful. So the routing on the motherboard swizzles. So it goes A to B to C to D to A to B to C to D. So that way, even if you have 2 devices that have interrupt A only, when you put them side by side, one will assert A and one will assert B. So with swizzling interrupts, you improve your performance slightly. And it was relatively easy to implement on the ASICs and FPGAs at the time. It wasn't too demanding, it was pretty slow. But on the downside, all devices shared the exact same electrical lines. And what that means is you could throw 255 devices on a bus, but electrically that's never going to happen. The clock speed's pretty slow, 33 megahertz. They tried adding 66 megahertz mode, still pretty slow. 32 bits is relatively narrow. They tried adding 64-bit. Clock skew, they discovered that while parallel is nice, you can run 32 bits every clock cycle. Your clock rate cannot increase to keep up with that, otherwise you'll start getting skew between each of the lines, and you won't be able to scale much past, say, 150 megahertz or so. Bandwidth, RAID controllers, high-end DD cards, if you had like a dual-port DD NIC on PCI, it's going to saturate the entire bus, and you're going to be bandwidth limited by your bus. It kind of evolved into PCI X. So PCI X is not PCI Express. PCI Express is mostly referred to as PCIe. PCI-X basically doubled the width. It registered all the I/O pins. So before, your I/O pin just went straight into the silicon. Now you hit a register, so you take a clock cycle delay, but you could run the bus up to speeds of 133 megahertz. The theoretical max is a gig per second. And the major software change was MSIs, which is on the next page. We'll get to that in a second. And they didn't bother making a PCI X 2 and 3, but by that time PCIe 1, and nobody bothered with it except for compact. So
we all know what happened to that.
exactly, right? So a lot of people here, if you mess with microcontrollers at all, some people, and you're probably used to that having like 32 interrupts or so. Well, PCI, the super duper computer bus, only had 4 interrupt lines. And that's awful. So every time you got an interrupt, you burn some cycles. The CPU's like, okay, which one of you guys was it? To figure out who actually raised the interrupt. So with an MSI, which is a message signal interrupt, the device can actually post a message to host memory that says, hey, here's an interrupt, and by the way, I'm the guy that raised it. So it improves interrupt performance vastly, and you don't have to do this, which is really, really sad when you consider like an EVR has like 32 interrupt vectors, if you so desire. So serial is the future. Basically around the same time, the late 90s, everyone's like, hey, we need to go to serial, because it turns out it's easier to run fewer bits at a really high speed than a lot of parallel bits at a lower speed. Silicon process advancements kind of helped a ton. It got really cheap to build SeriDESs, which are serializer, deserializer. So basically it takes in like 8 bits of parallel data, shoves it out in a high-speed stream of bits, and then the deserializer takes your high-speed bit stream and turns it back into 8-bit, 16-bit, 32 bits of data. So IDE PATA went to SATA, PCI went to PCI Express, and then we replaced serial ports and parallel ports with USB. So we all went to serial.
Forever.
What's that?
RS-232 forever.
Actually, we're going to have a whiteboard, so using that to illustrate too. So yeah, so the legacy PCI bus, basically, you had PCI bridge. Everybody shared the same data lines. PCI Express, it's a point-to-point, like each slot goes back here, here, here. So PCI introduced major software and major physical layer changes. The nice thing is it retained compatibility with the legacy configuration space, so the first like 250 bytes are still the same, But if you remember the whole capability pointer thing, if you're a PCI device, you just say, hey, keep reading these capability pointers. And it's software. Software doesn't need to know the difference, and sometimes it can't even tell the difference. It doesn't care if it's a PCI card or a PCIe card. And it can even emulate, if you want it for some weird reason, you can emulate int A, int B, int C, and int D. The physical layer, now we're driving many high-speed lanes instead of a parallel bus, and the links are now point-to-point. So the software, PCI Express was the one that extended config space to 4 kilobytes, and capability pointer 34 is what points to PCI Express. And the cool new thing is with PCI you have to do the weird config space registers, read and write. With this you can just memory map the entire configuration space. So if you had the theoretical maximum number of devices, you need a 256 meg block of memory. I don't think you're raising your hand.
Sorry.
No, it's cool.
Can you just compare and contrast like a POTA 16-bit connection with 16 PCIe lanes? What's the difference between a lane and like a...
Yeah, I'm going to get those in a few slides.
Oh, okay.
So, yep. Good question. Yep. Yeah. So on like on my platform right here, I know my PCI base address is E million hex. So with that, I know the maximum size of each of these. I can quickly say, if I'm talking to this device, I just go to address like E10000, and I know I'm talking to bus 2, and that's the entirety of its config space. So this is the capability structure for generation 1 and generation 2. So compared to PCI, you can control, you get status registers for the device, the link, and the slot. And this is important to point out because without any extra chips, you can hot plug PCI at will. You can, on some advanced servers, you can actually multicast and have 2 RAID controllers doing the exact same thing, and you can yank one out, put it back in, and software will happily handle it. No stoppage whatsoever. And then link control, you can actually bring down and reset the links without rebooting. You can change speed without rebooting. And then slot control, you can actually change the amount of power allocated to a slot. You can put it to sleep. You can get hot plug surprise event notifications. And all this stuff is just tucked away in this little, like 64-byte structure. And that's all. And that's for any PCIe device can implement any of these bits. So PCI Express also has a huge amount of software changes because it's now packet-based instead of address data line-based. So similar to networking, there's a transaction layer, there's a data link layer, and then there's the physical layer here, which is the RX and the TX. And now let me see if my projector explodes as I try to switch out of the presentation temporarily. Actually, it does. That's awesome. Oh, no, actually, I'm going to move on to those. So this is actually a copy of the PCIe spec, which is actually not publicly available, and I think it's a few $1,000s, so don't get pictures. So the TLP basically, what's that? I did actually, yes. So the field's present in all the where's the thing? So basically the transaction layer packet, there's a few different types of transactions, and here's the important part right here. Basically there's memory, read and write, pretty self-explanatory. There's I/O read and write, which is same thing but for I/O space. There's configuration, so these are your config space accesses. And then there's messages, which include message signal interrupts, configuration messages, so if you want to do like the power allocation, things like that, you change that via message there. And then PCIe has a whole host of advanced capabilities too. There's like advanced error reporting, so you can let the server know. And most of this stuff here is all server stuff. There's no reason for this to be on the desktop. Advanced error reporting, so you can report exactly what's going on with the link to your host OS. Virtual channel is really interesting. Within like a single logical link, you can actually prioritize and do QoS within that link. So you can have like a virtual channel 0 for like your super high priority stuff, and then you can have a second virtual channel for some less important stuff, and all within a single link, which is kind of interesting. Dynamic power allocation, so if you detect like your chassis heating up or something, you can start powering down cards. Then multicast and advanced reporting infrastructure and a few other, there's a lot of tricky features available that a lot of people don't bother with, because when people do bother with it, they usually do it wrong, which makes everyone's life really, really hard. Okay, yeah, so physical layer stuff. So there's basically at a minimum, there's an RX pair, a TX pair, and a reference clock. So in your point-to-point link, basically, if you have a transmitter and then a receiver, you're basically, there's two TX lines going this way, and then there are two RX lines going this way. And then out of band, there's a differential clock going this way, which is 100 megahertz. So it's always point to point, and it's packet based, and this is it. There's no like frame signals or anything. It's just this data link here, and then a 100 megahertz clock. And the clock phase doesn't really matter unless you're doing spread spectrum. All that matters is that you're as close to 100 megahertz within a few ppm, so it can perform clock data recovery on the incoming data stream. So all it knows is that it's getting this super, super high speed stream of bits going in, but if it has a known reference clock of the proper frequency, it can synchronize on the bit stream and it can recover and decode the data from that stream. And I think this is like the super brief, like kind of electrical look at it. And this all kind of drives up costs for consumer stuff, which is a little important. Since they're differential pairs, it requires a controlled impedance, so it turns into a bit of a transmission line. So it's vendor specific, but usually it's anywhere from 85 ohms to 100 ohms. So what this means when you lay out a board is based on your stack up, you need to have a very specific width and gap between the pairs, otherwise it doesn't work. Depending on the vendor, you can actually get almost 1.5 feet on just plain copper traces from point A to point B. The transmitter requires capacitors to AC couple it, so if you have a GPU or something, next time you look at the connector, you'll probably see pairs of caps right at the edge of it. Those are your transmit lanes. And the spec actually requires devices to handle reversal of PNN internally, because otherwise layout would be really, really painful. But some devices, depending on how advanced they are, if they're a multi-lane link, they can actually handle you reversing the order of the lanes too. Bandwidth-wise, and this is what you were asking, I think, Todd. So a single Gen 1 link, which would be a single TX pair, a single RX pair, is 2.5 gigatransfers per second in each direction per lane. So that's 250 megs. Gen 2 is doubling that, so that's 5 gigatransfers each direction per lane, 500 megs. And then Gen 3, the most recent one, is 8 gigatransfers in each lane, but that increases bandwidth to almost a gigabyte per second in each direction. So most smaller cards, like USB add-in cards, sound cards, will never go past a by 1 link, which is just 1 lane. Graphics cards are by 16, so take these numbers and multiply by 16. And these are all backwards compatible with each other too. So the latest graphic cards, which are Gen 3, will run in Gen 1 and Gen 2 slots. They'll just run at the slowest supported speed. And then you probably notice here these kind of weird numbers. So the data encoding here is 8B, 10B. So this is needed because if you send a whole bunch of ones in a row, then your signal starts looking awfully like a DC level on the bus. So what 8B, 10B encoding does is it takes a 8-bit SIP number and encodes it into a 10-bit symbol such that you're guaranteed a minimum intervals of 1s and 0s, so you don't suffer a DC bias on the lane. But as you may have noticed, this is an extra 2 bits, so this adds a considerable amount of overhead. Whereas in Gen 3, they switched to 128B, 130B, which is why these numbers got a lot wider apart. You're only doing 3 more gigatransfers per second, but your bandwidth nearly doubled because they changed the data encoding. And then there's in depth, they also added, this data is also scrambled here too. There's a lot of advanced tricks they did to use the similar physical interface but kick up speed quite a bit. And there's a few sideband signals for like JTAG and power, but for all practical purposes, PCI Express is just a lane and then 1 clock per lane. And that's all it is. It looks different. Here's a Gen 1 link I captured off the scope. So what you're looking at here is, it's called an eye diagram. And at the receiver, you solder a probe onto it. And basically this is just sampling at 80 gigasamples per second, and it's basically taking the bit stream and overlaying it over each other so you can, it's important for integrity purposes, you can see what the width of the eye is and what the height of the eye is. If either of these shrink too much, then your receiver has no idea what's going on and your link fails, essentially. So this is Gen 1, which is about 250 picoseconds per eye there, per unit interval. Yeah, this is all super cheap to make now, which is kind of ridiculous. At some points, you actually need to worry about like the propagation speed of light when you're designing these things. This is Gen 2, and this is part of the compliance test. This is what we call a mask, and basically you never want, if this hits the mask, you're out of spec. So in this case right here, it's meeting it pretty handily there. And then Gen 3 is a newer and interesting beast. It looks pretty. This is at 8 gigatransfers per second, so this is actually a 33 gigahertz scope. And what Gen 3 does is, in order to get these speeds, actually there's equalization involved. So the signal without equalization, this is like shrunk down to maybe the size of this, and the receiver actually applies some pretty advanced equalization techniques to reopen the eye. And this is also, you can run this data stream at much higher bit rates across the same copper interface. So I think the equalization stuff's probably a little too much for this, but if you want to ask me about it afterwards, I'd be more than happy to rant about it. So the physical media is, everyone's motherboard here. There's by 16, by 1, by 4. You can run a by 16 card in a by 1 slot. Sometimes people like Dremel out the rear of this. There's also idiots on forums who will Dremel off the parts of their card, which is really funny to watch. They'll get like a brand new GTX and then they'll just like Dremel off the card instead of the slot, and it's terrible. And then also on your laptop, there's mini PCIe, which is also actually the same connector for mini SATA, but this replaced mini PCI in the laptop scene. Express card does have PCIe on it. It also has USB on it, so Express cards can be both USB and or PCI Express. And then a lot of people use, for backplanes like telecom, you can actually run PCI Express over like telecom blades and stuff. And the spec allows you to go all the way up to a by 32 link, which you'll never see on a desktop, but some telecom blades will have gigantic line cards that are like by 32 at Gen 3, so insane amounts of bandwidth. You can actually do PCI Express over fiber also with just a standard SFP or SFP Plus that you're laying around with some pretty terrible regular fiber too. But theoretically, you could run your GPU a few houses down, and a little bit of fiber, and your computer won't ever be able to tell the difference. So, and that's the actually, I should have thrown something about Thunderbolt in here. But is everyone familiar with Thunderbolt, the new Apple spec? So basically, Thunderbolt combines a PCIe by 4 Gen 2 link with DisplayPort over copper wiring. So everyone was finally hoping that there would be a decent way to have a laptop and have like a giant GPU. So the problem is Gen 2 by 4 is still only 2 gigs of bandwidth, which isn't enough for a lot of high-res gaming. But they're hoping if they ever go to fiber in the next generation Thunderbolt, or if they can go to Gen 3, then maybe you can finally have a laptop and then a little docking station so you can play all the games and have a laptop. So maybe sometime soon that may actually happen. So time check wise, it's 12. Oh, this PowerPoint's really cool. It's actually on the slide. So it's 12:30. I can do some questions and stuff now, or people, if there's a preference, we could go over like Linux PCIe stuff, or we could play around with some FPGA PCIe stuff.
I have a question.
Yeah, sure.
The external connections, I've got some switching gear that claims it's PCI, but it's copper, fairly thick cables off the back. Is that
PCI or PCIe?
I'm sorry, PCIe.
Yeah, you can do over copper cabling as well. I think it's some pretty beefy copper cable.
Yeah, so is there just running the lanes between the boards, or is some sort of external transfer?
There's probably a redriver or something, and then there's running the physical lanes across the cable. Yeah.
So with the PCI Express, the PCIe card rather runs the lanes, does it treat those like a bunch of channel mounted network lanes?
Yes, yeah, so basically, yeah, so let's say you have like a whole bunch of memory writes to post, and you have 4 lanes, it'll parcel them, it's kind of striping basically, it'll stripe them across all available lanes. And
So you can have kind of, they can be uneven data rates between them.
yeah, exactly, yep. So when you do layout though, it's pretty tolerant, but the lengths of each of your lanes in like the multi-lane device need to be within a few inches of each other. but the inter-pair spacing, like the P and the N, are really, really close to each other. And generally, if you're doing something with like a connector, you take, like, if the spec says 0.5, you give yourself a budget of 0.25 on the board, because the add-in card guys might have screwed up, and you want to give them some budget as well for the link, so.
Now, is it possible to dedicate a lane to a function?
No.
So it's always.
Yeah, so the lane's always gonna hit the device,
Okay.
and then